Okay, this is the final section of part 2, where we discuss abstract fluctuation theorems for Markov jump processes. Here is a warning. Things looks complicated here. But I tell you that everything is just formal, straightforward, and trivial. Okay. But anyway, I think it's not very easy to understand because I'm not going to discuss any physics here. We will simply derive these relations just formally. And then we apply them to physical situations in part 3 and 4. So here we have to go through formal discussion. But anyway, let's get started. So we consider a general Markov jump process with this transition. This is a collection of transition rates for any k and j and any t. And here is one additional assumption. We assume that for any j and k, which are not equal, and any t in this interval, this is equivalent to this. Okay, this means that whenever you can go from k to j, then you can go from k to j. No, j to k. If you cannot go from k to j, then you cannot go from j to k. Okay, so that is our assumption. That is the only assumption. Then with this assumption, we formally define something called entropy production. Of course, in part 3 and 4, we discussed that this has physical meaning as entropy production, but here this is just the formal definition. Entropy production from k to j is defined as the log of the ratio of this transition rate from k to j and the transition rate from j to k. And so this is a typical jump quantity. Okay, this is defined only when you have jump. And also, if you switch k and j, okay, I have to discuss this. So this is defined on, of course, this is defined only when this is non-zero. When this is 0, we set theta to be 0. Okay, and if you switch k and j, then you switch this and this, so you get minus. So you get this relation. So this is antisymmetric with respect to this indices k and j. Okay, and if you take log of this, you get this. Okay, well, this is basically equivalent. Now, so this is just a jump quantity. So let's take a path, gamma, described like this. And I defined the quantity called total entropy production along the path, gamma, like this. Okay, so this is the uppercase theta, which depends on omega tilde, and it also depends on the path gamma. And this is simply the sum of entropy production along this path. And so in this path, there are n jumps. So for each jump, you just compute this entropy production and just sum over. Okay, so and actually, you can define this also as a path quantity, as I did before. So from this, you define this path quantity, and if you integrate, you get this. But anyway, in this part, this description is easier, and this is enough. Okay. Now, I define something called time-reversed Markov jump process. Well, this is something very simple. So we have this transition rate, and then we define its time reversal, omega tilde dagar, this way. It's a collection of transition rates like this, and this is simply defined like this. So this is basically the same as the original transition rates, but the only we parameterize this with a different parameter, time parameter. And actually, we have seen this S before. So t is the standard parameter for time, and it goes from 0 to tau. And then this S goes backward from 0 to tau like this. Okay. And yes, so yeah, this is reverse time. And then the corresponding escape rate is simply the sum of this. And so this is related to the original escape rate this way. And so, yeah, the only change is here, this time coordinate. So if omega tilde is time independent, if this does not depend on time, then there's no change. So in that case, this omega tilde and omega tilde dagar are the same. Okay. That was the time reversal of Markov jump process, and this is something more drastic. We consider time reversed path. So suppose that we have a path like this, then gamma dagar, its time reversal is really the time reversal. So this this path starts from J0 and ends at J4. So this time reversed gamma dag R starts from J4 and ends at J0. And everything is flipped. So this, this becomes here, here, and here. Okay, and this is the definition. Okay. Here we have J0. You just change the order, reverse the order, and write this like this. And here you do not only reverse the order, but you just do the same transformation, and you really reverse the time like this. And so this defines this new path. It's a real time reversal. It really goes backward. Okay. And of course, it's very natural to introduce new indices k, and also this Sm like this, and then these are written in this way, simply. Good. And now this is an important quantity of the total entropy production. And recall that we have this relation. And theta, uppercase theta, is simply the sum of theta. So if you go backward, you get minus in this entropy production. So the total entropy production along gamma is exactly the minus of the total entropy production along gamma jag R, this time reversed path. Okay. Of course, here you have to also reverse this thing. But anyway, we have this anti-symmetry. Okay. Now we derive, this looks complicated, but we derive a very important fundamental relation called the detailed fluctuation theorem, this one, okay? And what is this? Well, this is transition probability density that we introduced before, okay? So we examine the left-hand side. So we have, first of all, this transition rate, transition probability density. And this is defined in page 40. So let's look at page 40. Yes. So we define the path here, and this is the transition probability density. Yeah. And this is basically the probability density of the path when it starts from J0. Okay. And probably you remember, but the definition is that, it's first we have this staying probability at J0 and this transition rate, staying probability, jump rate, and so on, and staying probability here. And this is easy to understand, and you can compare this with this picture easily, but mathematically, it's better to write it this way, okay? And be careful, here you have m, here m runs from 0 to n, like this, and here m runs from 1 to n, okay? But if you look at this picture, you understand this. Okay, so let's copy this and paste it here. Okay. So this is the expression of this transition probability density. And now e to the minus theta. And for this, we should look at page 47 to 5. Well, that's quite recent. 2 is this, and 5 is this. So we want to have e to the minus theta. So we simply want to have e to the something, and then e to this is simply this, okay? And then you will see that this is exactly written in this way. So we have transition rate from Jm to Jm minus 1, and then this is the reversed one. And actually, this is the original one, Jm minus 1 to Jm, and this is reverse transition rate, okay? And everything product. Now, we consider this combination because there occurs some cancellation, big cancellation. Look, this part and this part, they are exactly the same. So they just cancel. And we get this rather simple product here. Okay. Now we want to rewrite everything in terms of reversed language, reversed path and reversed protocol. Okay. And now this is the staying probability. And this is the original expression. Now we rewrite this in terms of new variables. So first of all, we have this S variable, and this lambda Jagan is defined in this way, and we have this K and SM defined like this. So if you plug all this definition in here and carefully compute, and this comes here and this comes here and so on, this is very elementary, but rather tedious computation. But I did it. I did it carefully, and this is correct. But anyway, it's nice to check. It's nice that if you could check. So this is correct. And then this is a very this is nothing but the formula for expression for the staying probability in this reversed language. Okay, so this is just a standard staying probability with this hopping transition rates omega tilde Dagar. And as for omega, this is simply basically this thing, okay, and with this, okay, and then you can just rewrite this like this. So you plug in here this one and here this one to rewrite this like this. Okay, not yet the end, because this the order of product is not very natural. So you redefine M and you sort of count M backward from M to 0. And then you can rewrite this exactly like this. And also this one exactly like this. And now, again, tedious but elementary calculation. And then this has precisely the form of this one, right? Or this one in page 40. So we can rewrite this as a transition probability density for gamma Dagar, the reversed path, with this transition probability and transition rates. Okay, so this is what we have proved. Okay, and this is called the detailed fluctuation theorem, and this should be compared with this relation. This is just the definition of theta, but this says that the transition rate from K to J and J to K are related like this with e to the minus theta, the entropy production. And here it's kind of similar. So here we only have K to J hopping, but here we have path. And here we have J to K, but here we have reversed path. And instead of this, we have this total entropy production. Okay. So in some sense, this is much more refined version of this thing. Good. So this will be the source of many things. And we first derive something called the integrated fluctuation theorem, which is here. So this says that if you consider the path average of this weird quantity, you get 1. So this is, in a sense, Jauchinsky equality type relation, very general relation. Okay. First of all, let P0 be an arbitrary initial probability distribution, and we assume that it's non-vanishing, it's non-zero for any J. And Q, this is strange, Q doesn't have any physical meaning. It's just an arbitrary probability distribution, again, with the condition that it's non-zero for any J, okay? Then you consider this weird quantity, exponential e to the minus total entropy production minus log of P gamma initial, this is the initial state of the path of this probability distribution, plus log Q gamma final. Okay, everything is in exponential, and then you take the path average with this initial distribution, and of course transition rate omega tilde. Okay, and then yeah, okay, let's rewrite this carefully. So you sum over all paths, and this is the probability density for path gamma, and here we have this, and now we have e to the minus log P gamma. So this means that you get this. And you have e to the plus log Q gamma, so you have this. Okay? So this is from the measure, and these are the quantity to be averaged. But now we did this intentionally, but now you see that this guy and this guy cancel. Okay. And let's rewrite this. Now we want to rewrite this in terms of gamma dagar. Okay. First, we note that d gamma is the same as d gamma dagar. This is not something we comes from Liouville's theorem, but this is just trivial because the sum over gamma is simply summing over all the states that a path visited, and also you integrate over time sequence of times, jump times, and that this kind of summation is exactly the same if you do it for gamma or gamma jaga. So this is simply written like this. Okay, and as for here, we can use the detail fluctuation theorem. Okay, so this becomes this. Okay, and this is equal to this, and this went away, and here this is this. Okay, we had gamma final, but in the reverse path it becomes gamma jaga initial. Okay, final state become initial state. Okay, so now gamma daga is simply a dummy index, so you can just rewrite it as gamma. So this is equal to this thing. And then this looks very nice because this is nothing but the probability density for path gamma in a process with transition rates omega tilde daga. Okay, so and the initial distribution is Q. Okay, so this is of course by normalization, this is 1. So we have proved this in this relation, exact relation. We still don't see any physical meaning here, but we will use it later. And actually, for example, the Jautinsky equality comes out of here in certain setting. Okay, so this was the integrated fluctuation theorem. Finally, we discuss, okay, this is the final page. We discussed the fluctuation theorem. Here, for simplicity, of course, you don't have to assume this, but I would like to assume this for simplicity. We consider a Markov jump process in which omega tilde and omega tilde dagar are the same. For example, if omega tilde is time independent, we have this. But of course, you can have time-dependent omega with this symmetry if you have some reflection symmetry in time interval. But anyway, probably this is the most important case. So anyway, we assume this. And you take an arbitrary initial distribution, probability distribution with this property. Again, this property. It's non-zero for any chain. Then we consider this weird quantity. Well, it's kind of similar to what we had here. But now we have psi is defined as theta gamma plus log of p gamma initial, this thing, and the same distribution minus log gamma final. Okay, and actually here we have to have omega tilde and also omega tilde. But since I assume that this omega tilde and omega tilde dagar are the same, I thought we shouldn't. Actually, it's here, but we don't have to write it explicitly. So I just omit this omega tilde. Okay, and then we consider this probability. So we put this psi gamma inside delta function, and so this is the probability density that psi gamma is exactly equal to some real number s. Okay, the delta function psi minus s, and we take the expectation value over all paths. Okay, and actually here is a mistake. Yeah, this is omega tilde. Oops. This is omega tilde. And so, yeah, I think I already said this. Now we want to show that this satisfies this familiar fluctuation theorem. Okay. To do this, consider this combination. And first of all, I write down the definition of P of S, which is this. But to be explicit, this is written like this. This is precisely this one. First of all, this is the integration measure for path, right? This is a probability density for path, and we sum over this. And here, this is this, okay? And e to the minus s. Since we have this delta function, you can write e to the minus s like this. Good. And now we want to rewrite this. And first of all, we use this definition and yeah, we write this in terms of theta and p. Okay, so this becomes e to the minus theta times this and this. Okay, so this is exactly equal to this, and everything else is still the same. And now we use first of all use the detail fluctuation theorem to rewrite this like this. Okay, and this is whoops, this, yeah, and then this guy and this guy cancel each cancel, and you get this, you put it here. Okay, and this is this, so we get this. Okay, now we want to rewrite everything using gamma Jagar. Okay, and again, this is can simply written like this, and gamma final is equal to gamma Jagar initial by definition. And here, I use this assumption, so omega tilde Jagar can be written is exactly the same as omega tilde. And now, finally, I have this. So psi for gamma Jagar is equal to minus psi gamma. And this comes from, this antisymmetry for theta. And of course, in this case, these are different, but in our case, they are the same. They are the same. So yes. And of course, if you switch gamma and gamma Jagar, these are switched. And since the sign is different, the signs are opposite, so you get this you have this antisymmetry. So this is written like this. Now everything is written in terms of gamma Jagar, and you will see that this is nothing but the probability that psi gamma psi is equal to minus s, okay, minus s. And so this is p to the minus p of minus s, and so this is equal to this. So you can bring this here to write down this familiar form of fluctuation theorem. Okay, so this is the end of part 2, and see you in part 3.